Columbia and Eagle were on their way. At stake, nearly 10 years of research, development, and fabrication. Some 20,000 companies throughout the United States participated in the building of the Saturn V rocket and Apollo spacecraft, which carried astronauts Armstrong, Aldrin, and Collins on their historic journey to the moon.
The astronauts always hated guidance and navigation. Press one button and you'll go to the moon. They were pilots, damn it. The last pilot instrumentation laboratories had was a monkey. Yet here, standing in front of Apollo, they were trained to press the button and go. But how do these systems go? How do you get from the Earth to the moon using just a sextant and the stars? It's August 1961, and Richard Batten thinks he has an answer to this problem. Batten was in charge at Instrumentation Laboratories, the lab given the task of designing the navigation, guidance, and control system that would take Apollo to the moon. And taking Apollo to the moon had two big problems. One, how do you know where you are accurately? This is called the measurement routine. And given that, how do you know which thrust to apply? This is called the navigation filter. The navigation filter wasn't so much of a problem because Batten had a good solution in perturbation theory. We won't dwell on that today. Instead, we're going to focus in on that measurement routine. What Batten needed and what he didn't have was a way to recursively and accurately measure where you are using the ship's sextant and inertial sensors. So what is a recursive state estimator? Let's say you have some ship state, the speed of the ship, the position in space, etc. Let's call that xt for the state at time t. The job of the recursive state estimator is to estimate that from two quantities: the previous state, xt minus 1, and any sensors that you happen to have. Formalizing this a little more, we can imagine there's some model A that takes the state xt minus 1 and can guess the state xt. For example, if the state was a car at a position on the road, the model to go from xt minus 1 to t would be the speed and the time. But our ship isn't only standing still. We're also trying to move it, applying thrusts to move it along. These thrusts are our control. Pressing on the gas in the car, for example, just like with the previous state, there's some model B which can go from the control input and show its impact on that state, xt. This is all great in theory, good models of the system, but now we get to the real world. We're going to just add a disturbance term for friction for anything else we didn't account for so far in the system. And this is the model method to generate your state xt. There's another way, however, to generate your state xt. You could just measure it. You can have sensors tell you, with some error, what the state is. The following equation shows you how to go from a sensor reading to that state xt. But again, we need to add some noise indicating that the sensors in the system might be noisy. The job of Batten's team was to compute this xt, the position in space and speed of the spaceship, given yt, some space sextant angles of the stars that you could get. But they were running up against a wall. Everything they could think of was either computationally expensive or just infeasible. What they needed was a new approach. This is when Stanley Schmidt enters our story. Stanley Schmidt was the head of NASA, and he had stumbled on a recent paper, A New Approach to Linear Filtering by Rudolf E. Kalman. He looks at the paper and sees that's exactly what he needs. Immediately invites Kalman over to come explain his filter to NASA scientists. The Kalman filter is broken down into two steps, the prediction and the update. The prediction is where we use the model we have of the process to guess where we should be, and the update is where we incorporate sensor data to get a final predicted state more accurate than the model or the sensor alone. Let's go over the prediction in more detail. We'll start with the equation that we had in the earlier section to guess the state at time t. Let's assume it's a perfect world and the next state just follows from the previous step in the control. We're gonna leave this disturbance term in right now, but we can't know it, so it has to be removed. To do that, let's add a second variable, pt. pt represents the uncertainty in the process. I call it variable. It is really a normal distribution around your guess state, representing how uncertain you are about that guess. Let's imagine it as a Gaussian cloud around the updated state, representing the set of options the true xt might be. So pt minus 1 represents the uncertainty we used to have around state t minus 1, but to capture the uncertainty we're going to have around state t, we need an extra term. We call this term q, and it's essentially that disturbance term moved into the pt equation. It's a Gaussian representing the amount of disturbance your model might have in it. If q is large, your model's probably inaccurate. If q is really small, you have strong belief that your model is accurate. Okay, now that we're done with information from the model, let's move to measurement and add information from the sensors. First, we do the same thing we did in the last step. We get the measurement assuming no noise, CT. It's represented by those red dots around our green true state. Similar to above, however, we have to account for the measurement noise we can possibly get. We're going to represent that with the red Gaussian, with the spread, Wn. However, similar to PT, we have to incorporate our noise information about our measurement to understand how much measurement to add in versus how much model. We're going to do that with the following equation. This is the Kalman gain, and it's the heart of the Kalman filter. Notice that PT is both in the numerator and the denominator, and there's a new term, R. R represents the measurement noise, and we're going to add it to the denominator for now. So you can notice when the measurement noise is large, Kalman gain is small. If our model Gaussian is large, Kalman gain will be big. Also, notice that it can never go over 1, it can never be less than 0. Fundamentally, the way to think about Kalman gain is like a probability. It's measuring the probability of whether the model is right or the measurement is right. Let's use our Kalman gain and update our state. So we see in the state update, if we add k Kalman gain to our sensor guess and identity minus Kalman gain to our model. So we mix the two to get a more accurate result. We then just do that to the model representing the Gaussian, modeling how uncertain we are about this new step. Now we have built pretty much exactly what NASA wants. It provides you a simple update that takes you from a state at time t minus 1 to the state at time t while adding all the sensor information and accounting for some amount of error that you might get. But I do want to give you a better feeling for these R and Q matrices we've pulled out to control the Kalman gain. I've said they model disturbance and sensor noise, but let's watch what they do with an actual system. We'll start with a system with a small q and a large R. We can see that this produces a small Kalman gain, indicating we're pulling more from the model. And as you can see on the graph, even though the measurement is all over the place, the Kalman estimate quietly matches the true state. Conversely, in a system with a large q and a small r, lots of belief in our measurement, little belief in our model, we can see on the left that the posterior Kalman belief stays tight, even though we have very little faith in our model. So let's try modeling our system badly. Let's say we have a lot of belief in our measurement, but our measurement is actually usually wrong. You can watch the Kalman filter below follow the measurement over the model. So let's go back to 1961. NASA's engineers have just been wowed with a version of the same talk you just got. Kalman's filter was worked on for the next 6 months, and a version of it gets added to the Apollo guidance computer and helps in the fight of Apollo 11. It's upgraded and changed over time with several extensions, but it's used for the next 9 Apollo missions. It's used for radar tracking of ships. It's used in gamma-ray spectroscopy and oil exploration, real-time flow measurement, and online fault detection in nuclear power plants. It's one of the most ubiquitous algorithms in the world today.